Identifying the operations used to create equivalent systems of equations. So Alex has an interesting way of explaining these operations. I'm actually going to explain them in a very similar way, but I am also going to shorten the notation or the symbolism involved. First thing I'm going to do is actually state those elementary row operations. So let's define that. I'm going to use a definition, and that definition is actually on the vocabulary words of elementary row operations. Elementary row operations, capital O. And these don't have to be done in any particular order. Sometimes they're called single elementary row operations. And the reason for that is because you could only do one of these operations at a time. We are actually going to apply these operations to something called a matrix later on. So Alex gives these explanations to slowly give you the vocabulary words necessary to simplify matrices. And we're going to get to that. We're going to build our way up. We're going to build the language to these operations and to the simplification of matrices. Let's say what they are. One of them is one of the elementary row operations, or one of the single elementary row operations, is that you could switch any two rows. And I use the notation R sub I, double-sided arrow, R sub j. So if I had to switch, let's say, row 3 with row 35, I simply would write R sub 3, double-sided arrow, R sub 35. A second elementary row operation is we could multiply a row by any scalar except 0. No reason to multiply by 0. We can multiply a row by any scalar except 0. And the way I would symbolize this is by A times R sub I. For instance, if I need to scale row 5 by 6, I could write 6 times row 5. So that's an example of how to write such a notation. I will actually draw an arrow underneath it, saying that we will also store in row 5 as well. So the arrow underneath it will actually say store the new computation in row 5. So for those of you studying computer science, there are a lot of times when you need to create an entry spot or a storage location. So this is kind of mimicking that behavior. We need to store in a certain row or store something in a new location. One last elementary row operation, and that is we could multiply a row by any scalar except 0 and add to another row. This is sometimes called the addition method. You learn the addition method when you're solving linear systems as well. So we're going to multiply a single row by any scalar except 0 and add to another row. This has nothing to do with elementary row operation number 2. Has nothing to do with it whatsoever. The symbolism for this would be a times r sub I plus r sub j. And I'm going to write an arrow from left to right. And that arrow also means we're also going to store in where? We're also going to store in row sub j. So with numbers, it will look something like 3 times row 1 added to row 3 and then store in row 3. So notice what I said. That arrow just means store in row 3. And so that will create a similar system. Why don't I go ahead and pause this for a sec, or you go ahead and pause the video. Make sure you write all these notes down. You do need these definitions. You need to know that these are our 3 single elementary row operations, and you can only do them one at a time. Okay, you can only do, let's say, if I needed to do row operation 2 here, I only could do this one, and I can't do 1 or 3. If I needed elementary row operation 3 here, I can only do this one, and it has nothing to do with row operation 1 and nothing to do with 2. So keep in mind that 3 is not related to 2, and 2 is not related to 3. These are by definition the 3 single elementary row operations. My notation is a little bit different from what Alex explains. I think you will catch on. I'm sure you could catch on to Alex's notation as well. Mine is a little bit shorter than the Alex notation. I just use a single arrow, and Alex does a little bit of redundancy, but that redundancy makes things really, really clear. So why don't we go ahead and get started with this problem? The idea behind these elementary row operations is that we keep writing equivalent systems. We write one system after another, after another, after another. So if you started with 2 equations and 2 unknowns, we continue to write 2 equations, 2 unknowns, continue to write 2 equations and 2 unknowns. But notice it is getting simpler as we do elementary row operations. Let's take a better detailed look at this example. I do need to erase the board on the right, so hopefully by now you had a chance to pause the video and take notes. Let's go ahead and restart here. I'm going to erase this. So I already have the row operations memorized in my knowledge, right? After practicing it so much and so much, it becomes part of you. Okay, so that's what you're trying to do when you're studying. You're trying to practice quite a bit so that this language becomes part of you, even if it's temporarily. All right, so how do we get from system A to system B? We're going to consider system A. So system A says negative 2x plus 3y is equal to negative 7. And I am going to give you a hint here. Since you're going to be working with matrices soon, I highly recommend that you work down. So there's system A, and we want to know how do we get from system A to system B. The first thing you want to do is intuitively mark that as row 1 or equation 1, and this is row 2 or equation 2. So if I was using the notation before that I was indicating, I will simply call this row sub 1, and I'm going to call this row sub 2. But another way of saying that is really talking about equation 1 and equation 2. So how do we go from system A to system B? Not too difficult. What we're going to do now is negative 3 times row 2. And I'm going to write it right here. I'm going to write negative 3 times row 2 and then put an arrow underneath. Now I'm going to be very, very neat. I'm going to line up my x's going straight down, and I'm going to line up my y's going straight down. Neatness counts in mathematics. It actually helps you prevent a lot of mistakes. The first thing we're going to do is we're going to keep row 1. Row 1 is not going to change. So we're going to do negative 2x plus 3y equals negative 7. And so you can see that the elementary row operation performed here has no effect to row 1. But we are going to change row 2. And row 2 is going to get a new equation. It's simply going to get negative 21x plus 12y is equal to 24. And so that is now what we call system B, according to what you're given. So what would you do to answer that? According to this, we did negative 3 times what? Row 2. So it would be right here, right? We didn't add anything. We simply did negative 3 times row 2, and then it becomes the new storage or new equation in the second row. So my notation is quite different, but Alex here is being accurate, but we're going to abandon on all these A2s, B2s very, very soon. But for now, that's what this means. The symbolism over here on the right simply tells you to put a negative 3 here, and then multiply that by row 2, and that becomes your new row 2. So you would bubble that as your answer. Circle that or bubble it and put a negative 3 here. Why don't I make it clear? I could do this. Ooh, no, I could do magic. Whoa, bye-bye. I could put a negative 3 here and then circle it. So the key here is that you practice writing this. Don't just bubble the answer. Even though you could see the answer in your head, make sure you write this. Get used to writing these x's all the way down. Get used to writing these y's all the way down. Get used to writing all these constants all the way down to practice your neatness. You're preparing for matrices. Now, how do we get from system B to system C? Well, once again, row 1 didn't change, and the effect happened to be on row 2. What happened here? How do we go from here to here? So temporarily eliminated y. That's what it looks like. So how can we temporarily eliminate y from system B? So we're going to do something called negative 4 times row 1, and then add it to row 2. And then I'm going to draw an arrow from left to right that says I'm going to store in row 2. Let's find out what we have now. Notice, according to our elementary row operation, row 1 does not change. That's negative 2x plus 3y is equal to negative 7. And then we're going to do negative 4 times row 1 and then add it to row 2. No problem, piece of cake. 8 added to negative 21, negative 13. And then negative 12y, negative 12 times y plus 12 times y. That's 0y. I'm not going to even write it. It's now equal to 28 add 24. And if you add 28 and 24, we do get 52. And there, we now got system C. So to answer the second part of the question, how do we transform system B into system C? Well, there it is. There's the answer. It's negative 4 times row 1. And then we're not going to store in row 1. We're going to store in row 2. So negative 4 times row 1, add it to row 2, and then store in row 2. So Alex does do a very, very good job noting this. It's just really confusing with all these B sub 1s and B sub 2s and C sub 2s. We're going to abandon this. I promise. Even Alex is going to abandon this. But for now, if you're just matching the game or trying to understand the rules of the game, that's what this question is about. Do you understand definitions and do you understand the rules of the game? Elementary row operations. We are not storing in row 1, we are storing in row 2, so it's got to be this one. It's got to be this third choice. And then we just need a negative 4 And let's put a -4 here. -4 times row 1 plus row 2, and then store it in row 2. That's an explanation of what's going on with these vocabulary questions. These are really vocabulary questions. So make sure you understand elementary row operations, memorize them, and you'll be using them over and over and over and over and over again. All right, let's move on. Let's go ahead and walk through this example here. It's kind of strange. There's notation that's already given to you. The system of equations is right here. The system of linear equations is at the top there. It says enter the augmented matrix. We're certainly going to do that. And so what we're going to do now, instead of writing the x's and y's over and over again, we're just going to write a chart that will actually symbolize the rows. And then we'll just rewrite an equivalent system every single time. And eventually we're going to get a solution to the system of linear equations. This is sometimes called Gauss-Jordan Elimination. And with Gauss-Jordan Elimination or Gauss-Jordan row reduction, let's say a Gauss-Jordan elimination for a 2x2 system. Our end goal is something like this. It doesn't always happen though. Our end goal is to get a staircase pattern of ones and with zeros in between. And then this could be a constant and this could be a constant. Doesn't always happen. And the strategy is often, this is our first thing that we want to get, is a leading 1 in the first row. And then we want a 0 right underneath that leading 1. And then this is going to be third, and this is going to be fourth. Now, how do we get to these numbers? We're going to use something called elementary row operations. So if you're following along from the previous video, let me just recap what these are. You could switch any two rows. So r sub I could switch with r sub j. You could scalar multiply any single row as long as what? A is not 0. And then you're going to store in that same row. Okay, you're going to store in that same row in the new system. You could also do what? You could also scalar multiply. I guess I could use a different letter. You could scalar multiply a single row and then add it to another row and then store it in that new row r sub j. So those are our 3 elementary row operations. Let's go ahead and get started. Unfortunately and fortunately, this example actually tells you what operations to use. It's sort of weird, but eventually you're not going to you will not get a walkthrough. You'll just be given a system and then you go ahead and perform the elementary row operations to your best ability. Let's go ahead and get started. I'm going to first mimic what's being asked. The first thing you do is write the matrix. I'm going to write it right here. I'm going to try to write it in a similar font size. -5, 20, -9, 40. And to augment this, you simply draw a little dotted line to separate your constants. Now keep in mind, each row is still representing an equation. Now, how do we get the leading 1 in the first row? How do I get the leading 1 in the first row? What do you have to do to the -5 to get the leading 1 in the first row? And you can only use an elementary row operation. So in this case, we are going to do a -1/5 times row 1, and then we store in row 1. I'm going to introduce a new symbol. This symbol is called tilde, but in this case, tilde means what? I'll tell you what that means. This symbol here means two words. It means row equivalent. So in this context, it's not similar. You may have seen that symbol used in geometry, and in geometry course, that is called similar. But in this context, when we're working with matrices, we are using tilde to represent row equivalent. Now, do negative 1/5 times row 1, and we get a leading 1 here. And then we get a negative 4. And then we also get an 8. And notice only row 1 changes. And now we just copy row 2. Sometimes you'll see me just copy row 2 first. How do you get the 0 underneath the 1 here? How do you get this to be a 0? So what we're going to do now is pivot from row 1. We're going to do 9 times row 1. And then add it to row 2. So row 1 doesn't change, and then row 2 does change. Once again, we do tilde. Tilde right here. And so row 1 doesn't change. I'm just simply going to copy it. And then we have 0. And then we have negative 36 plus 40, which is 4. And then 72 minus 80, which is negative 8. So notice we got the leading 1 first, and now we got the 0 right underneath the leading 1. Our goal now is to get this to be a leading 1 in row 2. We want this to be a leading 1. And how do we do that? How do we get this 4 to be a 1? We are going to, what do you think? Got to scalar multiply row 2. And what should we scale it by? Scale it by 1/4. And then we're going to store in row 2. Once again, we write the tilde symbol, row equivalent. Row 1 doesn't change. And we have 0, and we have 1, and we have negative 2. This is getting pretty. Now, our 4th position. So we get this to be a leading 1, then we get a 0 underneath, then we get a 1 here. Now we work back up here and get a 0. Dun, 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 dun. How do we do that? Now we're going to pivot from the bottom. For row 2, add it to row 1. This time, we store in row 1. But since row 2 doesn't change, I'm going to copy row 2 really quick. 0, 1, negative 2. I copied it really quick. Now we're going to change row 1. This will be a 1. And then 4 times row 2 is 4. 4 added to negative 4, you get 0, and that was done intentionally. And now we also have negative 8 plus 8, which is 0. Ta-da! Now, how do we read this? Well, we back substitute. This actually says y is equal to negative 2 and x is equal to 0. Now, how do you write your solution? This is poor, to tell you the truth. This is a very poor way of writing a solution. The problems with technology. The way you write this is this solution set only consists a unique solution. So we write a set notation, and then we write parentheses to symbolize an ordered pair. This is a unique solution, and the unique solution is a single ordered pair, 0, comma, negative 2, and then you close it with a set brace. So this, how do we say this? This is a set consisting a unique ordered pair. This is singular. There's only one and only one solution here. There's only one ordered pair that would satisfy this system. I'm going to briefly check it in my head here. Let's see if it works. Yes, it does. It works for the second equation. And does it work for the first equation? Yes, it does. Wow, that was a quick check. But it's not about getting the answer here. It's really about the journey. It's really about understanding all your elementary row operations and figuring out how to use it to get this nice staircase pattern, which is what we call Gauss-Jordan elimination. Let's circle our final answer. But more importantly, can you replicate the work? Do you understand all this work? Do you understand how neat you have to be and how precise you have to be? Every X is down in one column. Every Y is down in this column. Every constant is down in the same position. Like I said, neatness prevents mathematical mistakes. So work on the neatness, work on your vocabulary, work on your journey. Go ahead and solve this system of linear equations using Gauss-Jordan elimination. Hopefully by now you have memorized the 3 elementary row operations. And for a 2x2 matrix with Gauss-Jordan elimination, our goal is what? Our goal is to get this nice staircase of ones. Those are not hashtags. That's my way of writing constants. But typically this is the strategy. It does not always work, but our first goal is to get that to be a 1. Our second goal is to get this to be a 0. And our third goal is to get this to be a 1. And then the fourth goal is to get that to be a 0. Like I said, it doesn't always work. There's other ways to get there. So that doesn't always work out in this particular order. But generally speaking, I would say 7 out of 10 times this procedure really works. First, second, third, fourth. What else am I going to say? The other thing you want to do is avoid fractions as much as you can. So don't introduce fractions early on into the system. Maybe introduce the fractions in late, but try to avoid fractions as much as you can. First thing we want to do is convert that system into a table called a matrix or an augmented matrix. So for this class, we simply write a bracket, 5, 45, dotted line, right where the equal signs are, and then negative 50, 9, 83, and then negative 96. So if possible, try to get that leading one in the first row. Not a total surprise. It is possible here. So these numbers are designed precisely to get you to practice the vocabulary. Understanding the rules, or the vocabulary of elementary row operations. Boom, 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 boom. We're going to do what? 1/5 times row 1 and store in row 1. Make sure you write tilde on your paper. Tilde means row equivalent. And we are changing row 1, so 1, 9, and then negative 10. Remember, what does 1/5 times row 1 means? It just means this. It's just shorthand for saying multiply 1/5 to both sides, right? That's all that's going on. It's pretty cool because you're being very, very neat. You're keeping all your x's in one column, y's in another column, and your constants in another column. So work down. Work down when you're working with matrices. Work down, work down, work down. Do not work across. All right, what is row 2? Row 2, 9, 83, and negative 96. Our goal now is to get a 0 underneath that 1. So we're going to pivot from row 1, negative 9 times what? Negative 9 times row 1, add to row 2. And as soon as I write that arrow from left to right, that's going to say store in row 2. Row equivalent. Row 1 doesn't change. I just recopy that. Draw your dotted line. And we're going to change row 2. Made that purposely to be a 0. This will be a 2. And then 90 plus negative 96 is negative 6. We're at the third spot already. Can we get this to be a leading 1? And the answer is yes, we can. Yes, we can. Can you kick it? Yes, we can. All right. So 1/2 times row 2 and then store in row 2. Once again, write tilde to symbolize row equivalent. Be very, very neat. Row 1 doesn't change. Dot, 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 dot. Negative 10, 0, 1, negative 3. Ta-da! And then finally, can we get a 0 in the in that 4th position? And that is certainly, why not? Definitely. Negative 9, row 2, added to row 1. Draw the arrow from left to right. We're going to store in row 1. Now, row 1 changes, so instead of doing row 1 first, I'm going to just recopy row 2 to prevent mistakes. I don't have to think so hard. I just make sure that I just copy row 2 correctly. Now, we're going to change row 1. So 27 minus 10, which is 17. Ta-da! Now, how do we read this? You always back substitute. Read it this way. So y is equal to negative 3. X is equal to 17. You got to trust me. Always read it this way. Because you will not always get a unique solution. What's really interesting about these is when you get a dependency solution. We'll get to those. All right, let's write the solution now. This is a set consisting a unique solution, and that unique solution is called an ordered pair. Once again, this is a set consisting a unique ordered pair. Boom. Let's let's try that again. Let's graph this system of inequalities. The first thing we're going to do is graph the associated lines. So here is going to be an associated line in y equals mx plus b form. And this one's going to be solid. How do I know this is going to be a solid line? There's an equal sign right there. You could actually see it. And so that equal sign, it says less than or equal to, so it can equal to that line. So we're going to go ahead and shade that line. That's why we are going to make that solid. How about the second line? What does the second line look like? The second line is simply going to be 3x plus 4y is equal to negative 20. And this one is going to be dotted because there is no equal symbol in this inequality. So right here, it's just strictly greater than, so it's going to be dotted. Let's graph these lines. Graph these to the best of your ability. I'm going to need, let's see, a y-intercept of 1. And it does say to go down 3, right 4. So 1, 2, 3. 1, 2, 3, 4. So right here and here, we're going to connect those dots and plot a solid red line. Can we get, what can we get for the blue line? Using the intercept method, let's do the blue line really quick. So when x is 0, we get negative 5. When x is 0, we get negative 5. And we get a dot right here. And then when y is 0, we get negative 20/3. Not a problem. That's simply what? 6 2/3, negative 6 2/3. Yeah, negative 6 2/3. So when y is 0, well, negative 6 2/3, and then y is 0. Oh, did I say negative? Negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 6 2/3, and y is 0. So right about here. All right? Do the best you can. Take a straight edge and play connect dots. Oops. That should be a blue dot. Very interesting. Turns out these lines are parallel. Now we still need to graph the inequality, which means we need to shade. We always shade the true side, but there are multiple regions here. There's actually one region here, another region between the lines, and a third region above both those lines. We want to know if there's any true inequalities that satisfy both inequalities simultaneously. So what we do is pick a test point. Why don't we test the first inequality? We're going to pick tests. We're going to pick the test point 0, 0 for both inequalities. Let's start with the red one. Let's test this one. Y is less than or equal to negative 3/4 times x plus 1. Well, 0 less than or equal to 0 plus 1. True or false? True. So if that's true, we are going to shade below that red line. So we tested the original inequality that involves the red line. Oh, why didn't you guys tell me I made a mistake? What did I do wrong, guys? Ooh, why don't I change that eraser? Boom, 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 boom. How about that? Ah, I forgot to make that dotted, huh? You thought I forgot. Dun, 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 dun. Okay, so remember those are dotted. I can't shade the values on the line. Let's test 0, 0 for the original inequality, the original second inequality. Let's do that. So 3 what? 3 times x plus 4 times y is greater than negative 20. Zero plus 0, is that greater than negative 20? And the answer is yes, it's true. So we need to shade the 0, 0 side relative to blue line. So we're going to shade this way. We'll shade the 0, 0 side. Ah, look at that. Looks like we're done. Looks like we got what we wanted. We're going to have lines going this way for the shading relative to the blue line. And then we're going to have lines going this way. And that's where they both collide. So that's what we're looking for. We're both, it's true for both of these lines in this region. You could also pick another test point to verify this. In fact, the instructions say to do so. Then give the coordinates of one point in the solution set. Obviously, I could choose 0, 0 again, but that's kind of boring. So why don't we choose something that's more interesting? Why don't we choose, let's try this one. What's that? 1, 2, 3, 4, 5, 6. Let's try 6 and then negative 4. So let's test 6, negative 4. I guess I could test it up here so it doesn't look so confusing. Let's test 6, negative 4 and see if it's a solution. So let's test the first inequality. Negative 4, is it less than or equal to negative 3/4 times 6 plus 1? Dun, 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 dun. Negative 4, less than or equal to negative 9/2 plus what? 2/2. Is negative 4 less than or equal to negative 7/2? And the answer is yes, that is true. Negative 4 is definitely less than negative 3 1/2. How about we test the second inequality? Same thing here. Test what? 6 negative 4 to the second inequality. So 3 times what? 6 plus 4 times negative 4. Is this greater than negative 20? Let's find out. 18 minus 16. Oh yeah, that's definitely greater than negative 20. That is true. So it satisfies both inequalities simultaneously. The ordered pair, 6, negative 4, is a solution to this system of inequalities. I want to write that down. 6, negative 4 is a solution. And circle your graph. That's very, very important. Boom. One more thing to circle, and that is your test values. You probably should show this work. This is a good sense of, I'm sorry, this is good writing to communicate to somebody else. Let's graph this system of linear inequalities. So the first thing you want to do is graph 3 lines. And what are those 3 lines? You have negative 5x plus 6y is equal to 12. You have x equals negative 3. And then you have y is equal to 5. So you got to graph those 3 lines. And we need to know which one are solid and which one are dotted. The first 2 are solid, and the last one is dotted. Go ahead and take your graph paper, do the best you can here. You know, if you have a straight edge, take advantage of it. I'm going to create a t-chart for the very, very first equation. For negative 5x plus 6y is equal to 12. Let's do a quick t-chart here. So when x is 0, y is 2. And when y is 0, x is what? 12 over negative 5. That's about negative 2 2/5. No problem. So let's draw some values here. Do the best you can. Always graph, you know, by hand for these problems. These are not terribly difficult. So this is 4, negative 4. This is 3. This is negative 3. And let's graph our lines. 0, 2 is here. And then negative 2 2/5, 0. Right here, there's a line. I'm going to connect those dots. I'm also going to draw my horizontal line. This line right here needs to be dotted. That's the dotted line labeled what? Y equals 5. We also have a vertical line right here. This one is solid. That line is labeled what? X equals negative 3. And we also have the other line, which I'm going to take a straight edge and do, well, I don't need a straight edge. I'm good right now. So let's draw this line right here. And now we need to figure out the shading. Well, if you look at the vertical and horizontal, the shading is a little bit more obvious. So what are all the y values less than 5? It tells you to shade this way, right? So I just indicate that with a small arrow. What are the x values that are less than or equal to negative 3? Once again, I'm going to indicate that with a small arrow. The less values are always on the left, right? So left of negative 3. So there's a small arrow going that way. I probably need, oh, that's enough. Well, here, I'll need one more little small arrow right there. So the small arrow is telling you which way to shade for the vertical and the horizontal line. Now we just got to test this blue line, or test this original inequality. Let's pick 0, 0. 0, 0 is not on that line. So let's test 0, 0 and see if we need to shade it. A negative 5x plus 6y is greater than or equal to 12. If you test 0, 0, we get 0 plus 0 is greater than or equal to 12. Well, that's false. So shade away from the 0, 0 side. So that means we got to shade up. Now, what are we looking for? We're looking for where all the arrows actually find something in common. You know, which region has all the arrows in common? I think I see it. I see it. So there's some black here. There's some red here. And there's some blue, right? And there's some blue because of that little blue arrow right here. It says to go this way. And so where all of them are true simultaneously, that becomes the set of solutions to this system of inequalities. There are actually an infinite number of solutions. Could you name at least one of them? If there's an infinite number of solutions, could you please try to name one of them? And I'll leave that as that. You did graph the solution. What do you need to show here? The best thing you could do is show all three lines and they're plotted correctly. And then show your test value. Show your test point. This would probably be really good communication right there.